Question 4. Compounds J and K are found in plant oils. We are seeing J here. It has an aldehyde, it has an alcohol, and then a ketone. Okay. Then K here has a carboxylic acid and also has an alkene there. So complete table 4.1 to state what you would observe when J reacts with the reagents listed. Now, here 2,4-dinitrophenylhydrazine, this one tests for the presence of the carbonyl compounds. So there is a ketone, that means we shall get a positive test for that. And also this one, positive test. So that means we are going to have an orange precipitate. Orange precipitate. Sometimes you can say red or yellow. Okay, it depends on what you're seeing, but majorly we use orange. Okay, then TOLLEN'S reagent. TOLLEN'S reagent gives a positive test for aldehydes, okay, not ketones. And this one has gotten an aldehyde, so that means there will be a positive test, which is actually the silver mirror. Silver mirror. TOLLEN'S reagent is called ammoniacal silver nitrate. Okay, then sodium metal. So when the sodium metal reacts with an alcohol, we get what we call sodium alkoxides. So you remove this one here, you put the sodium, plus, minus, and then the hydrogen here it comes off as a gas. Okay, so we get half a mole of hydrogen gas. So that means here we shall just put effervescence. Effervescence. You need to be careful with the spelling. Effervescence, or if effervescence is very hard for you, put fizzing. You hear something like fizzy drinks when you open the septs, something like that. Then Roman 2, J has two optical isomers. Optical isomers are non-superimposable. Okay, so draw the three-dimensional structures of two optical isomers of J. Now here, that means it must have a chiral center. Where do we see a chiral center? A chiral center is that carbon, which is connected to 4 different groups. There is 1, 2, 3, and 4. All of these ones are different. So when we are drawing, I will put the carbon here. It doesn't matter which group you're going to put where. Okay, but what is important in 3D is to show, they said 3-dimensional, you must show the wedge, the one that is facing you, okay, this one here, and the one that goes away, that goes in the plane, that goes in the board. Okay, this is 2D, but I want you to look at that 2D. So where you are right now, the one that is a wedge here is the one that is facing you. Okay, this one is facing you. And then the one that is going away is this other one here. Now, it doesn't matter which one you are going to put where, which group. So I can decide to put an OH here. Then I put the CHO here. I can have a CH3 here. Then the other one is a ketone. Yeah, there is this one, COCH3. So I can put here the COCH3 like that. Then I put this one this side, put OH here. Then because this one is a mirror, then this one will appear to be coming like this. Then I will put CHO, something like that. And then this wedge here, you can shade it. And then I'm going to put which wedge? I mean the group CH3. Then this other one is COCH3. This one this way. So the one which was far away from the mirror line also appears to be far away from the mirror line. So as simple as that. But then since you are reflecting in the mirror line, don't write this C here. Okay. So when you are writing it here, you also write like this, because of course it has to be You know, it has to be facing, just like you can look in the mirror and then your nose is the one you see other than you seeing the back of your head. You see that? So this one remains as a carbon like this. Part B, K is used to make the addition polymer, perspex. A synthesis of perspex is shown in this diagram here. Okay. Now, this one, they react with reactant L, and then we see something like this. But you can see this is a carboxylic acid. This one comes to an ester. That means they reacted this one with an alcohol. All right? And the alcohol is this part here. So that one has to be methanol. You put something like this. Let us put the H here, then the O, then the CH3. So the alcohol loses the hydrogen, then the carboxylic acid loses the OH, like that. So identify L, set the conditions required for this. So the L has to be methanol, CH3, OH. Conditions, there has to be an acid there, and then you hit under reflux. So we can say acidic. Conditions, acidic conditions, then heat under reflux. So the acid, we can put maybe sulfuric acid, HCl, like that, especially sulfuric acid or phosphoric acid. Then Roman 1, draw one repeat unit of the polymer. So we are going to have this one here. So this one breaks off like this, and also this one goes like this. Okay, so what then are we going to have? We shall have a carbon here, then a hydrogen, then now one single bond because this one has been broken, and then COOCH3, then CH3 here, then you open this here and also there. That is the one repeat unit, and you are done. Roman 3, use information from table 4.2 to suggest how the infrared spectra of M and perspex would differ. Explain your answer. Now, this one is very, very, very simple. This one here, we are seeing there is no double bond here. The rest are there. These ones are there. So there is no double bond. Now, M is an alkene. This one is no longer an alkene. It doesn't have the double bond. So what I will do, I will go to the absorption where there is an alkene. So for alkene, we are seeing it here. Okay, 15001680. Okay, so there are since there is no double bond in perspex, that means that perspex would not have absorption at this, okay, in this range, but it would be there for M. As simple as that. So I would say perspex, then they are putting something like that, R, would not have an absorption, peak at 1500 to 1680 per centimeters, because it has no carbon-to-carbon double bond. Or you would say that M would have an absorption here because of this. Okay? Reverse is true. Roman 4, K can be made from propanone in the 3-step synthesis here, shown in this. Okay, we have propanone, then this is hydroxy nitrile. That means here they added hydrogen sulfide, hydrogen cyanide in trace amounts of, let's say, potassium cyanide or sodium cyanide. Okay, it's an addition reaction. And then from here, there is hydrolysis. We can see this one here going to a carboxylic acid. So they put like maybe dilute HCl to give you this one here. And then from there, now there is an OH here, then a carbon here which has gotten a hydrogen has to lose one hydrogen, and then we are seeing an alkene here. So that simply implies that to reduce an alcohol to go to an alkene, we can use concentrated sulfuric acid, or we heat this one with aluminium oxide. Okay, so that is that. Now, what are they saying here? To complete the table, to identify the reagents used and the type of reaction in each step. Now, for the first one here, like I said, hydrogen what? Cyanide. So I'll put hydrogen cyanide, or you can put potassium cyanide, whatever. Type of reaction, this is an addition reaction. And then let's go to the next one here. For the second one, here I said from this one to this one here, that is hydrolysis. So I'll write here hydrolysis. And then the reagent we are using here is an acid. Okay, I can put an acid. It can be HCl. It can be sulfuric acid. Okay, but usually we use HCl here. So I will just put H plus, meaning an acid. Okay, then aluminium oxide here. Yes, like I said, it can give us the alkene when you react it with an alcohol. So this one here is an elimination reaction. Elimination. Or if you don't say elimination, you can say dehydration, because they remove water from there. Dehydration reaction. So this has been it for this paper. Thank you so much for watching. May God bless you. If you find the content very helpful, kindly like, share, and even subscribe. See you in the next videos.